Hey everyone. So in this video, we're going to look at a second example here. In the first one, we looked at employees at an accounting firm, and we talked about how to write the null and alternative hypothesis, which is something that we did last time. But then we went into how to calculate our p-value, which is basically just the probability that this sample mean could have happened in the context of the larger problem. If that probability is smaller than the significance level that we've set for the problem, which we have to set first, then we reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. We haven't proven anything to be true. We haven't done anything like that. All we've done is not shown sufficient evidence that this is a statistically significant difference. And so the difference that we're seeing with the sample versus the population is all within the realm of what's considered normal. I'm doing air quotes here. Normal, because things vary, data varies. That's just what happens. So here we have the U.S. Department of Agriculture reports that the mean cost of raising a child from birth to age 2 in a rural area is $9,405. You believe this value is incorrect, so you select a random sample of 900 children, age 2, and find that the mean cost is $9,290 with a standard deviation of 1,540. At a 0.05 significance level, is there enough evidence to conclude that the mean cost is different from the $9,455? So again, we need a null hypothesis. So we're just going to call that H0. Our null hypothesis here is that the mean cost is $9,405. That's what the Department of Agriculture says. That's the historical mean. So we're going with the status quo for our null hypothesis, our H0. Our alternative hypothesis is that the mean is just not equal to 9,405. We don't care if it's smaller or that it's bigger. All we care is that it's not 9,405. So this is a two-tailed test. And if I were to draw the normal curve, we would be satisfied to reject the null hypothesis if this value were either larger by a certain amount or smaller by a certain amount. So now let's actually find what that amount is. So we need to set up what our x value is, our mu, our standard error. And again, this just becomes a regular problem from the last unit. We're trying to find the probability that x is less than or greater than a certain amount. That's all we're trying to do. So in this case, x is our 9,290. Our mean was the 9,405. And our standard error is the standard deviation of the population, which we don't have. So we're going to use, since we're looking at 900 children, that's a very large N, we can say that the standard deviation of the population and this sample are really close together. So the standard error would be 1,540 divided by the square root of N, which in this case is 900. So there's my standard error. All right, so now, how do I figure out the probability in this problem? So we don't know exactly, we're looking at a normal distribution like this, but we want the area on both sides, right? Okay. So this sample happened to come back less than the mean. So I'm going to see what's the probability that I'm outside that range. What's the probability that I'm less than 9,290 if my regular population has a mean of 9,405 and this standard deviation, what's the probability that I would be outside of that range? Just to the left side. I know that sounds like a one-tailed, but just to the left side, I get a probability of 0.125370 blah blah blah. Okay. Now, this would just be the probability on this left side of my curve. So I also would find the probability that something would be above that. So I need to double this amount. So I'm going to take, for the two-tailed test, I'm going to take the probability I got and multiply it by 2. And so now my p-value, this is the probability that x is less than 9,290, or that x is greater than whatever that same distance from the mean would be above the mean. So this is about 115 below. So this would be like 9,520. So the probability that both of these things happen, remember an OR probability, we just add together the two probabilities. And so since it's the same probability, because it's a mirror image, because it's symmetric, we're kind of bringing together everything we learned this semester. We're going to end up with a probability of twice this probability. So in this case, we have 0.025. And so what that means is that that is less. This is less than 0.05, which was originally our significance level, which again, we have to pick our significance level before we calculate any values to be ethical in our tests. So in this case, since the probability is less than the probability I was expecting, we reject the null hypothesis. And we accept our alternative hypothesis. Now, those are two different statements, okay? You can reject the null hypothesis without saying that the alternative hypothesis is true. All we're saying now is that, you know what? I think maybe the historical mean that we've had is no longer the historical mean, and that's okay. So we're rejecting the null hypothesis. So if we're rejecting the null hypothesis, there's only one type of error I can have here, and that is type 1. So what could happen is we're saying that the mean is not 9,405 when in fact it is. And in the context of this problem, I don't think that is detrimental to anybody. But we're rejecting the null hypothesis, which means finding a sample with a mean so low cannot be attributed to statistical variability. So it has nothing to do with the fact that data varies, because if we were going to take this sample out of the mean, if we were going to do that process several times, take 900 children and do this whole process, the mean of that sample should never really fall this far away from the mean of the population if that population mean was indeed the population mean. So what we're basically saying is if this were normal and we took a bunch of samples, we should never expect to see anything this far away from 9405, which then tells us maybe 9405 is not the right value for the mean. All right, we're going to do one more example here. This time we're given some data. The number of years it took a random sample of 32 former smokers to quit permanently is listed below. At a 0.01 significance level, is there enough evidence to reject the claim that the mean time it takes smokers to quit permanently is 15 years? So we have 32 former smokers, and this is the amount of time it took them to quit permanently, listed here. So my null hypothesis, H0, is the fact that we are, the report says it takes 15 years. So that's the claim, okay? So we're going to say mu is equal to 15 years. And we're just wondering, does this data support that? Or does it give us enough evidence to say, you know what, I don't think that mu is 15 anymore. So the alternative hypothesis would be that mu is not equal to 15. But it doesn't matter less than or greater than. This is, again, a two-tailed test. So what pieces of information do I need? Well, normally I have an x, I have a mu, and I have my standard error. Well, all I have here is mu. I know that I'm assuming that mu is 15, and so I need to know what x is. Well, x is going to be the average of this sample of 32 smokers. So I'm going to find the average, the mean, of that data set. And that comes out to 14.83. The standard error I'm going to find by first finding the standard deviation of this data set. So that's stdev.s. This is a sample, it's not a population. And so the standard deviation is going to be 4.287, but that's not the standard error. The standard error is the standard deviation divided by the square root of the sample size, which in this case is 32. So the standard error is 0.758. Now at this point, if you have an intuitive understanding of normal distributions, we can see that within one standard deviation of this mean is this population mean. And so I think it's going to be hard to reject the null hypothesis here, but let's go ahead and calculate the probability that x, since this x value is less than the mean, we're just going to say, what is the probability that I would be outside of this range? And we calculate that by doing norm.dist. This value, comma mean, comma standard error, comma true. And so this comes out to 0.413, which would already be large enough to reject to not reject the null hypothesis. But remember, this was a two-tailed. This is two-tailed. So at the end, I have to multiply my probability by 2. And so this comes out to 0.827, which is much larger than the the significance level of 0.01. And so we fail to reject the null hypothesis. There is not enough evidence. There's not enough evidence to suggest that it does not take 15 years to quit smoking permanently. I would almost say that this data confirms the fact that it takes about 15 years to quit smoking permanently. All right, well, that's all of the examples that we're going to go over. We did a one-tailed test. We did a two-tailed test given the mean and the standard deviation. And then we did a two-tailed test just given some data where we could calculate the mean using our average formula and the standard error using our standard deviation formula and the square root of the sample size. I'll see you in the next one.